Okay, so I was just talking about studies on like human studies, and I was just talking about retrospective and prospective studies and some of the challenges with that. And this will be the challenge with any kind of non-controlled experiment. So usually if you have a controlled experiment where you can have like experimental group and control groups, and you're controlling everything about the experiment in a very controlled environment, that's going to be very different from these type of studies where you're looking at relationships and correlations. There's going to be other factors that you couldn't control that you have to gonna have to tease out. So that's not just in human studies, any kind of not experimental kind of experiments that's gonna deal with this type of drawbacks. So what determines how much? So we talked about how in this one how dose, the concentration, affects the the mortality or the lethal levels. So what happens? What affects these concentrations, right? Well, it depends on a lot of things, right? One of them is that how it gets in, right? So whether it's you're breathing it in, or you're drinking it from the water, or you're getting it from food, somehow you're getting it from the soil, maybe from the plants that you eat, your maybe babies are getting it from the mom, whether either through breast milk or during pregnancy. These are different routes of exposures or different ways in which these toxins can get into your body. And that's going to affect how the concentration as well, right? So like, you know, breathing it in might have a very different effect than if you were getting it from food or something like that. Okay, another okay, here's an example here. BPA. BPA is a chemical that's in plastics. It's an endocrine disruptor. They're found in plastics. They found that the main way that can so one of the ways that it can that could be people can be exposed was in babies, because they were in toys and bottles and food containers. This is what makes the plastic like a little bit more pliable, I think. So makes this plastic soft, which makes it nice for like soft, chewy toys and you know, food containers and things like that. So it's not so hard. So it's found a lot in. I'm sure it's found in other plastics too, but if it's made for babies, then they tend to get into their bodies more. So this is the reason why the BPA in baby food containers and baby toys has been pulled off the market, just because of the concerns that it could affect the little kids, the babies. Another factor that affect how toxins might accumulate, or the concentration of toxins, is solubility, right? How soluble that compound is in water or in fat. So you can have things that are not more polar, and they tend to be more water soluble, in which case they tend to kind of don't stay in the organisms, because the organisms kind of tend to flush it out, right? It just goes wherever the water goes. But that means it's gonna contaminate the groundwater or contaminate the surface water, so it's in the water, right? So that might affect. So if a toxin is soluble, then the routes of exposure might be more through water, not from the air or from the soil. If it's fast soluble, so tend to be non-polar, then they tend to accumulate more in the soil, and then also they tend to be stored in tissues, especially in the fatty tissues of organisms. So they don't get flushed out of their system, so they stay in the bodies. That's called bioaccumulation, right? So over the lifetime of the organisms, as they are eating or living in the water where the toxins are, they're slowly accumulating these toxins in their bodies, and over the lifetime, it could add up. So that's bioaccumulation. And some of these toxins can also biomagnify in the food chain. And I know I've talked about this many times in different chapters. So bioaccumulation, let's see if I can find a So bioaccumulation happens when in the toxins in the environment might be very dilute, right? So it might be in the water itself or in the particles and in bacteria and things like that. And then you might have small organisms like phytoplankton might be feeding on them, right? And as they feed, they accumulate the toxins in their body. So they're bioaccumulating individual in here, right? Well, as these little zooplankton are fed by larger insects or larger zooplankton or maybe even small fish, they're eating many of these in its lifetime. So in each one of these organisms, it's going to accumulate more. So you can see the number of little dots represent the accumulation of these toxins, right? So they're eating a bunch of zooplankton, so there's a lot more concentrated in here. And then these guys are getting eaten by the fish, and the fish is eating a bunch of little, they look like dragonfly larvae, lots of little dragonfly larvae. So all the toxin that was accumulated in each one of these is now in the fish, and so now that it's more concentrated in the fish, and then that effect keeps going up the food chain to a point where when you get to by the time you get to the top predators, the concentration of these toxin can be pretty high. Right. So in this diagram, it's being represented by the amount of these dots, right? So the dots are more dispersed here and become more and more concentrated as you go up. In aquatic system, because the chain tend to be a lot longer, because the energy efficiency tend to be a lot better. In terrestrial system, you got grass and herbivores and maybe carnivores, so you don't have too many levels. But in aquatic system, they tend to be a lot longer. So usually when you hear about these biomagnification, tend to be like with fish and predatory fish, and even some of the mammals and birds of prey that feed on that. So you hear about mercury bioaccumulation, and the fact that you shouldn't eat too much tunas, because we're the top predators in that case, right? Tunas and marlins and those big fish tend to have a lot of mercury in them. There was an issue with PCBs that in the aquatic food chain that was affecting animals like dolphins and seals that were feeding on the fish, and they were having toxic effects on them by the time it got to these animals. So so that's biomagnification. DDT, mercury, PCBs, these are classic examples of compounds that biomagnify in the food chain. And I know I talked about this before. You need to know about DDT because this is kind of the classic example of biomagnification. And the fact that it was this one, DDT in the water, plankton to fish to more fish, and then you got birds of prey, osprey, eagles, and things like that were being affected by the DDT. They were making their shells very weak, and they weren't hatching. That was causing a decline in our birds of prey. It was Rachel Carson, who was this woman back in the 1960s, I want to say 60s, who brought attention to this whole phenomenon of man-made chemicals having environmental impact and their consequences on the ecosystem. Before then, in the 50s, chemicals were considered good things. Is something that, human has made and it makes our lives better. DDT was extremely important in eradicating mosquitoes. This is probably one of the reasons why we don't have malaria in the US is because of DDT. So it was a very important compound. So there was a lot of good things that comes with these chemicals, but there are also consequences as well. And Rachel Carson was the one who brought that to our attention. And because of that, DDT has been banned in the US, and it's also in the process of being eliminated worldwide as well. Persistence is another thing to consider when we're looking at these compounds. So it has to do with how long these things tend to stick around in the environment, right? Some things have a short half-life, so these are measured in half-life, just like radioactivity. And some of these has a very long half-life. So also like DDT stays 30 years in the soil, and that's the reason why they can really accumulate, because it's still there, right? We've also talked about CFCs, right, being having a very, it's a very persistent compound. It doesn't biodegrade, doesn't break down. It stays in the environment for a really long time. So the longer it stays, the more impact it could have. If it's something that is fat soluble like DDT, they can accumulate in the organisms and stay in the environment long enough to make it up the way up the food chain, and that is the concern. Okay, so now we have, once you have all this information, now we need to kind of do something with that information, and that's called risk assessment, right? So the risk assessment of environmental hazards. So this is kind of the progression of a risk analysis, right? And most of what we talked about goes into this risk assessment. So what do we need to, you know, what is going to come out of this, all this information is a risk assessment. So when you're talking about risk, there is the qualitative risk and a quantitative risk. The quantitative risk is the, the kind of the mathematics, the actual probability of something happening, and probability of exposure and things like that. But for the most part, when you're thinking about risk, it tends to be qualitative, right? Our judgment is based on, what we perceive as a risk for the environment, whether it's, very risky, not so risky, so not, or somewhere in between, so high, low, medium, and high, right? And a lot of our decisions are based on that. The problem with that, is called perceived risk, is not always very accurate, because what we think is what it actually is. We tend to kind of overemphasize certain things and not emphasize certain things. So for example, catastrophic events makes these events look really risky, even though they might be rare. So things like nuclear accidents, right? That seems really scary, and this is a reason why nuclear power plants are, generally people don't want nuclear power plants in their neighborhood, because they're so afraid of these nuclear meltdowns that could happen. But yes, these are it's a real threat, but really these things are like a 1 in a million type of thing. It's so rare. You can count on like one hand some of the major radioactive accidents that happen. And in the US, it's so few, like people, I don't think anybody actually really died from nuclear accidents in the US. So it's very, very rare. So but we tend to overinflate the risk just because the few that did happen was so catastrophic, right? And we also tend to downplay more everyday risks, things like smoking and driving. There's a huge risk associated with driving, and you think about how many people die in car accidents each day, or how many accidents happens per day, or how many people die from smoking. The risks are really high, and they're very, very real, but they tend to be downplayed because it's something, it's like an everyday thing, right? And also long-term risks tend to get ignored more often too. So for example, climate change is, it's a really good example. This is a real risk, and we've been, all the scientists have been saying this is gonna be a big deal. This is something we really need to deal with, but it really gets downplayed because it's not happening right now, or at least the effect isn't felt by us immediately, and it seems like such a long-term thing that seems to happen in the future, and very slowly, so we tend to kind of downplay that as well, right? So there's this graph is kind of showing you the probability of death in the United States, right? And then so the main reasons why we tend to die tend to be heart disease and cancer and stroke and motor vehicle accidents. So these are real risks, right? But then, people are, afraid to fly an airplane. Or people are afraid of bees dying from, or getting hit by lightning and things like that. These are very rare events, but, people might still be, you know, afraid to go outside when it's lightning, or, you know, don't want to fly and or would rather drive instead, which seems so silly because the likelihood of you dying from a plane crash is so little compared to likelihood of you getting into a car accident. But you know, people still so afraid of flying because, you know, if you hear about airplane crashes and people dying and things like that. Okay, so oftentimes perceived risk is not doesn't quite match the reality. You can also analyze things quantitatively, so you can actually have these statistics, right? So those would be, that would be the probability of harm, and then you multiply that by probability of exposure, right? So what is the likelihood? So what is the probability that so you being harmed by something? So being harmed by a nuclear disaster. Well, if you are exposed to it, the probability of getting harmed is pretty high, but the probability of exposure is really low. So the overall risk might be low because this is so low, right? So you know, you might have to do something like that to calculate the actual risk or the quantitative risk. Okay, but there's lots and lots of, there's so much data that you have to incorporate in order to calculate these things that it's hard to really, you know, have a real value to this for the risk. You gotta take into all these different the studies, acute and chronic dose response experiments, retrospective studies, what the concentrations are in nature, what the solubility is, what the persistence is, whether it magnifies or not. All these things have to kind of be incorporated into the risk assessment in order to, you know, make a, you know, a judgment. Here, case in point here, case study in risk assessment. This is actually kind of interesting. So this is talking about PCB in Hudson River. I just realized I ran out of time, so let me stop here and I'll come back.